alkanes. Right? When you are comparing nearly same molecular weights, if all are having nearly same molecular weight, then alcohols will be having higher boiling points than ketones than aldehydes. So we are comparing. They have comparable molecular weights. Any questions are up to here? Respond.
No, sir.
You have any questions?
No, sir.
Next, sir. Regarding chemical properties, we are done with physical properties. Now we are seeing chemical properties. In which the first type of reaction, nucleophilic addition reactions. Now I am taking carbonyl system, means C double bond O. Because of electronegative difference, carbon gets partial positive and oxygen gets partial negative. So when you take nucleophile preferably attack on carbon, making this pi bond to shift over oxygen. Then what you will get? There will be bond formation between carbon and that nucleophile, and oxygen gets negative charge. Now I am adding electrophile, any positively charged species. Now that positively charged species will go and attack over oxygen, correct? Then what we got? OE, that positively charged species here, right? Now octet formation is there. There is no electron deficiency, correct or not? There is no electron deficiency. All are getting octet configuration. So because of that octet configuration, they will become stable. Right? Now I am taking in another way. Instead of nucleophile, if I make electrophile first and then nucleophile. So I am taking C double bond O. First I am making electrophile to attack. Then where electrons are rich over oxygen, so electrophile approaches oxygen, then this oxygen will donate lone pair of electrons. Then what you should get? Then this pi bond will be shifted over oxygen, so carbon gets positive charge. Yes or not? All right, first oxygen donated lone pair man. So can I write O double bond O? Now only one lone pair left. Bond E, positive charge. Correct? Now what happened? This pi bond will be shifted over oxygen. Then what you will get? Carbon, oxygen, electrophile. And this carbon gets positive charge. Response, sir. Do octet got satisfied here or not? So this is incomplete octet, correct? Here also octet is complete. When nucleophile attacked over carbon, this option also octet satisfied. Here also all are satisfied with octet. But here, if electrophile attacks first, we are getting incomplete octet. If it is incomplete octet, whether it is stable or unstable, means which reaction prefers nucleophilic attack or electrophilic attack? Which attack will be preferred over carbonyl system? Means this will happen readily. And here, it is not preferable. That's why always carbonyl systems prefer nucleophilic addition reactions. Electrophilic addition is not preferable. Any questions, sir, in this? Say something.
No, sir.
No, sir.
Here I want to take one more note also. I'm taking one note here. I'm taking CH3, C double bond O, CH3. Instead of writing CH3, I'm writing CH2 bond H. This is withdrawing group. Next carbon is alpha carbon. Over that alpha carbon, hydrogens are there. Then these hydrogens involved in tautomerism. During tautomerism, what happened? This bond will shift here. This bond will shift here, and hydrogen migrates from here to this. Okay. To understand, I will do one thing. I will keep this here. Now, can I do like this? This will shift here. This will shift here. Correct or not? Then what you will get? You will get CH3. C. This becomes OH. And this becomes a double bond CH2. Yes or no? Is it equilibrium reaction or not? Equilibrium or not? Forward and backward. So what we call this as? Due to delocalization of electron cloud and small atom migrates from one position to another position, then we call it as tautomerism. If there is no migration of atom, only pi bond delocalization happens, then it is called resonance. Along with resonance, one atom got also migrated, then it is tautomerism. So this is, can I call it as keto-enol tautomerism? This is ketone group, this is enol group. That's why what we call it as keto-enol tautomerism. So tautomerism is an equilibrium reaction or not? So then it will have K equilibrium constant or not? K equilibrium. What is K equilibrium? Concentration of enol form divided by concentration of keto form. If a keto form is stable, then K equilibrium will be small. If K equilibrium is high, enol form is more stable. Right, sir? So generally, which is more stable? Generally, always keto forms become more stable. Why? C double bond O bond energy. Bond energy of C double bond O is high. And what happened in total in both cases? There is double bond between carbon and oxygen in keto form, and there is double bond between carbon and carbon in enol form. So if you compare that bond energies, C single bond O bond energy is approximately 84 kilocalories. C double bond O bond energy approximately 178 kilocalories. C carbon C bond energy approximately 83.1 kilocalories. C double bond C bond energy approximately 146 kilocalories. Now compare both. In enol form, there is C single bond O, there is C double bond C. C single bond O and C double bond C. Both combined, how much? 146 by 84. 230. Correct? C single bond O, C double bond C, both combined 230. Now come to keto form. There is C double bond O and there is one C single bond C. C double bond O energy is 178. C single bond C is 83. Both put together. Both put together. 260. So where I require more energy. Keto form have more energy than enol form. Means I need to break keto form, means I need to spend more energy. Correct? Means it is not preferred to convert into enol. That's why keto form is. So why keto forms are more stable means due to high C double bond O energy. This is the major contributor, right? Because of stronger C double bond O, keto form is more stable. Enol form is stable if and only if conditions. Extension of conjugation, intramolecular hydrogen bonding, aromaticity, relaxation of strain. In these cases only, enol forms are stable. Otherwise, keto forms are stable. Just a moment. Isomerism. Tautomerism. Tautomerism is also termed as desmotropism. Same molecular formula, and it is a dynamic equilibrium reaction. Reaction occurs in forward and backward. Migration of atom like acidic hydrogen. Two or more compounds exist in dynamic equilibrium due to shift of an atom from one position to another position. Both forms are functional isomers to each other. We call them as tautomers. Differ in electronic distribution and also a position of atom. We have taken same keto form, enol form, which is more stable. Keto form is more stable. Reason: C double bond O bond energy is greater than C double bond C bond energy. That's why keto forms are more stable. And it is equilibrium. Therefore, K equilibrium equal to enol form divided by keto form. If K equilibrium value is increasing, means percentage of enol is increasing, means stability of enol increases. As it is equilibrium, we can write a delta G naught equal to minus RT ln K equilibrium. If delta G is more negative, enol form is more stable. Generally, keto forms are more stable. Reason: multiple bond between carbon and heteroatom. Heteroatom means oxygen or nitrogen or so on. Enol forms are more stable if and only if condition. What is it? Extension of conjugation with intramolecular hydrogen bonding, aromaticity, relaxation in strain, polarity of solvent, temperature. As the temperature decreases, enol form increases. These are the conditions. We have taken few examples and experimental data also. Clear? We have seen few more examples. The tautomerism is favored by acid as well as base. So acid catalyzes tautomerism, base catalyzes tautomerism. Just to see that. Done? Online? Clear or not?
Yes, sir.
Different examples we have seen. Here tautomerism, in last case tautomerism doesn't exist. Reason: double bond formation is not possible at bridgehead. That's why tautomerism doesn't exist. If there are no alpha hydrogens, then also tautomerism doesn't exist. Correct? No. Coming back. I will close this. Now, coming to reactivity. Reactivity of carbonyl compounds. reactivity of carbonyl compounds. Now tell me which is preferred, whether they prefer to for nucleophilic attack or electrophilic attack. Which is preferable? Nucleophilic attack is preferable. So reactivity of carbonyl compounds. It is controlled majorly by two factors. One is inductive effect. Second one is steric hindrance. These two factors will control reactivity of carbonyl compounds. One is steric hindrance and another one is inductive effect. Minus I minus M groups enhances reactivity of carbonyl groups. Less hindrance enhances reactivity of carbonyl groups. Right? So reactivity of carbonyl compounds will be influenced by two factors. One, inductive effect. There, presence of minus I groups enhances reactivity. That is magnitude of positive charge. Correct or not? If there is minus I group, what happens to the positive charge over carbonyl carbon? For example, see this. If I take C double bond O, here I am taking halogen. Do halogen is minus I group or not? Then what happens to partial positive charge over carbon? Increases. This becomes partial positive. This is partial negative. Na? If there is minus I group, what happens to partial positive? Increases. Then reactivity increases. So this is first factor. Second factor, steric hindrance. Steric hindrance. As steric hindrance increases, reactivity decreases. Online, any questions?
No, sir.
No, sir.
Now I am taking different examples. Observe this example. Acetone, give IUPAC name of this compound, sir. What is IUPAC name of this one? Sir, 1, 2, 3, 4, man. Tube butanone, butane 2-1. What about this one? 3-methyl butane 2-1. Correct? 1, 2, 3, 4, man. 3-methyl butane 2-1. Now, sir, which is more reactive? Which is more reactive? First one or last one? CH3, CO, CH3. This is also CH3, CO, CH3 only. Instead of hydrogens, I have chlorine. Presence of more minus I groups. What they will do? Increase electron density, decreases electron density over carbon, so you will get more positive charge. Therefore, that becomes more reactive. So D is more reactive than D, more reactive than, yes, A, more reactive than B, more reactive than C. In case of B and C, as chain length increases or branches increases, steric hindrance increases, reactivity decreases. Any questions, sir?
No, sir.
I am taking one more example. Can I say compared to all aldehydes and ketones, formaldehyde is highly reactive. Reason? No hindrance at all. Correct? So this is more reactive than acetaldehyde. Will be more reactive than benzaldehyde. Will be more reactive than acetone. Acceptable, sir. Will be more reactive than, or take two ethyl substituents over ketone. So I'm writing ethyl, C double bond O, ethyl. Chain length increases, crowding increases, so reactivity decreases. Then what is the name of this one? Benzophenone. Response, sir. Can I call it as benzophenone or not? Reactivity order. Any questions in it? Yes, sir. If more crowding is there, then nucleophile cannot go and attack. Then reactivity decreases. That's all. Any questions?
No, sir.
So this is the reactivity effect of substituents over carbonyl compounds, right? Now we are talking about nucleophilic addition reactions, right? So to make nucleophile to go and attack, what should be the better condition? Presence of minus I groups, presence of less steric hindrance, both will favor nucleophilic addition. Now in which first one we are talking about addition of HCN. First reaction, addition of HCN. We are talking about first reaction only. Nucleophilic addition is the first reaction, which we will take side heading then A. Addition of hydrogen cyanide, HC. Now, which will go on to attack first, H plus or Cn minus? Which should attack first? Cn minus. Nucleophile should attack preferably. So I am taking carbonyl system, adding HCN. So I am writing HCN as H plus Cn minus. Now, which will go and attack first? Cn minus will go and attack over carbon. Oxygen gets negative charge, then H plus comes there. So product will be, you will have Cn here, correct? And this will convert into OH. So there will be cyano group as well as hydroxy group. So that's why we got it as cyanohydrine. Any questions, sir? Respond. Do you have any questions here?
No, sir.
No. I am making this cyanohydrine to react with water again on hydrolysis. If I do partial hydrolysis, what happens? if I do complete hydrolysis, what happens? If I do reduction, what happens? What I told you about cyanide group. I am doing hydrolysis. Cyanide means C triple bond here, right? If it is partial hydrolysis, what you will get? This will convert into amide, C double bond O, NH2. If it is complete hydrolysis, what happens? It converts into carboxylic acid. If I am doing reduction, what happens? This will convert into CH2, NH2. Response, sir, yes or no? No. Here the function group is carboxylic acid. Priority function group. Here priority function group is alcohol. So here priority function group is alcohol or not? Among alcohol and amine, alcohol is senior. Among amide and alcohol, which is senior? Amide is senior. Hey, IUPAC now just now we have seen, man. I will do one thing. See seniority order. Who is senior? Cyanide. Where is amine? Here is amine. Among amine and alcohol, who is senior? Alcohol. Correct? Among amine and amide, which is senior? Amide is senior. Correct? Observe. Compared to amine and alcohol, who is senior? Alcohol. Among OH and carboxylic acid, who is senior? Carboxylic acid. Among alcohol and amide, which is senior? Amide. Right? So, what is the name of this one? Amide is, next carbon is called alpha carbon. So, our alpha carbon hydroxy group is there. That's why we call this as alpha hydroxy amide. Amide should be priority, na? So, this is alpha hydroxy amide. Now, what about this one? Alpha hydroxy acid. This is alpha carbon or not? Function group's next carbon is called alpha carbon. So, this is alpha hydroxy carboxylic acid. Now, this is alpha, this is beta. Now, what we call it as? Beta amino alcohol. Correct? Beta amino alcohol. Any questions?
No, sir.
I am taking one example now. Of course, these reactions are equilibrium reactions. Reactions are slow and equilibrium reactions. Right? Now I am taking one example. I am taking acetaldehyde, CH3CHO. Acetaldehyde. What is hybridization of this carbon? What is this hybridization? sp2. So geometry is trigonal planar. As this is trigonal planar, nucleophile can attack either above the plane as well as below the plane. Both are equally possible. Correct? So I am adding HCN. If I add HCN, there will be equilibrium. Now tell me, do cyanide comes above the plane or below the plane? If it comes above the plane, you will get one form. If it comes below the plane, it's a mirror image. So what will be the product? Racemic mixture. Correct or not? Online, respond.
Yes, sir.
So I am writing COH here, hydrogen here. I am writing cyanide here. This is chiral carbon. And I am writing here racemic mixture. Now I am doing partial hydrolysis. Like earlier, I am doing same. Like earlier, I am doing the same thing. Now tell sir, what happened? What happened if I do partial hydrolysis? Cyanide group converts into amide. So product will be CH3, COH. This will convert into CONH2. This is hydrogen. Here also whether I will get racemic mixture or not. Right, we are taking racemic mixture, man. Therefore, there also I will get racemic mixture. No. If I do complete hydrolysis, what you will get? What I will get? If I do complete hydrolysis, cyanide will convert into carboxylic acid. According to Fisher projection, which group should be written on the top? Most oxidized group should be written on the top, correct? This COOH should be written on the top. I am writing Fisher projection. This is chiral carbon. Then longest carbon chain should be vertical. Over that, I have to write HOH. Response, sir. HOH methyl COOH. HOH methyl COOH. And this is chiral carbon. Here also you will get a racemic mixture. What is this called as? Lactic acid? Is it lactic acid or not? This is called lactamide. Now I am doing reduction. If I do reduction, this converts into amine. Right? So what will be the product? CH3. Next carbon CH, OH, CH2, NH2. This is the chiral carbon. Here also I will get racemic mixture. Response, sir. Any questions in this? Respond. So can I write cyanohydrins are the useful synthetic intermediates to produce other functional groups? Yes or no? By using cyanohydrin, I am able to create other functional groups or not? Other compounds or not? Right? That's why we are saying cyanohydrins are useful synthetic intermediates. Any questions online? Someone respond, please.
No, sir.
No, sir.
Next. This is addition of HCl. Second reaction, addition of sodium bisulfite. Second reaction, B. B reaction is addition of sodium bisulfite. Here also can I write Na plus and HSO3 minus? HSO3 minus is nucleophile that should go and attack over carbonyl system. Can I say HSO3 minus is bigger nucleophile? Then what happened? Steric hindrance plays a role. If there is any crowding over carbonyl system, then they will not react with sodium bisulfite. If there is a less crowding, then they will react with sodium bisulfite. Corresponding reaction. C double bond O allowed to react with Na plus and HSO3 minus. So this is the nucleophile, will go and attack, gives rise and forms. This is also equilibrium reaction. So what should be the product? HSO3 minus will go and attack, and this converts into O minus Na plus, right? So it should be carbon bond. Here it should be SO3H, and here it should be ONA. Response, sir. Right. HSO3 minus will go and attack. And this one, 1 minute, 1 minute. It should be, yes. O, SO2HR. Because it should be S double bond O minus Na plus bond OH. Now this O minus should go and attack. Correct? So I have to write it as O SO2H, right? Right. Sorry, Q something. Now, this hydrogen is acidic hydrogen. From here, proton can transfer here, and Na plus can transfer here. Right? Acids, sulfonic acids are more acidic. So that H plus will migrate. If it happens, what you will get? This converts into O, S double bond O minus Na plus, and this will convert into OH. Any questions? So this is that bisulfate addition product. Can I call it as adduct? Addition product means adduct. Addition product. We call it as adduct. Clear? So carbonyls with sodium bisulfite forms adduct. Addition product. Right? These adducts are crystalline and water soluble because they are sodium salts, right? So they are crystalline and water soluble. No. If I add acids or if I do hydrolysis, they will form carbonyls back. That's why, because these are all equilibrium reactions. If I do hydrolysis, this will get separated out. Therefore, this reaction goes in backward direction. Right? So with the dilute acids, they can be converted back to carbonyl compounds. Because of this idea, can be used for isolation or purification of aldehydes and ketones. Wherever crowding is less, this equilibrium moves in forward direction. Means this reaction is more favorable for aldehydes than ketones. If we take ketones, methyl, more crowding, na? So that's why this reaction is more favorable for aldehydes. Online, do you have any questions here? Respond. Do you have any questions?
No, sir.
No. I am taking a note. Ethyl, C double bond O, ethyl. Now tell me, do it can react with sodium bisulfate or not? No, it will not react because crowding. Similarly, if I take this, also cannot react. Similarly, benzophenone also do not react. Acetone react to some extent, right? So, etc. Do not react with sodium bisulfite, right? Due to, what is the reason? Due to steric hindrance. Any questions, sir? You have any questions, sir?
No, sir.
So aldehydes, to some extent, only acetone, to some extent, show this sodium bisulfate reaction. If the crowding increases over acetone, reaction will not occur. Next one, sir. Reaction with Grignard reagent. Reaction with alcohol, Grignard reagent, yes. So C, reaction C. This is also nucleophilic addition reactions one. Nucleophilic addition of Grignard reagent. First one. I am taking formaldehyde with RMGX. RMGX is good source of R minus. Now R minus will go and attack. This will shift. So it leads to followed by hydrolysis. So you will get HCOMGX R. This on hydrolysis, you will get primary alcohol. So formaldehyde gives primary alcohols. Acetaldehyde gives secondary alcohols. So except formaldehyde, remaining aldehydes give secondary alcohols. Example, I am taking acetaldehyde with RMGX. Can I write RMGX followed by hydrolysis? Why you have to write separate reaction again? First we are writing RMGX. Second we are doing hydrolysis. Product will be CH3 COH R. If it is ketones, all ketones give tertiary alcohols. Any questions online?
No, sir.
No, sir.
So you are done with reaction with alcohols. Sorry, reaction with the Grignard reagent, right? Now reaction with amines. Reaction with amines. This is also nucleophilic reactions only, nucleophilic addition reactions only. So next one, reaction with amines. They are also lone pair electron donors or not? Means again nucleophilic addition only, right? Now I am taking acetaldehyde as an example. Or some ketone or aldehyde group, something as an example, with NH2 having some other group here. That Z may be hydrogen or Z may be R or whatever it may be. Now nitrogen acts as a nucleophile. It will donate lone pair of electrons towards carbon. Then this bond will shift. H will go there. Correct? Respond. So you will get one equilibrium. Now what is that equilibrium product? Carbon. This will convert into OH and this will convert into NHZ. Response, sir? Now, if I heat, what happens? If I heat, H2O can be eliminated, right? So then what it will lead to? Carbon, double bond N, check. Any questions in this? Do you have any questions in this?
No, sir.
If you want to write that in more number of equilibrium steps, if you want to write that in more number of equilibrium steps, I can write that in this way also. Instead of writing Z, I am writing in this way. Done na? Both are same only. See this. I am writing this in another way. Here I am writing it as RNH2. I am making this nitrogen to donate lone pair of electrons. Then what you will get? What you will get then? Here carbon. Here what you will get? NH2 plus R. And this group converts into what you will get? O minus A. This converts into O minus. From here, that H can migrate here. Or from water, it can take that H plus and form OH. O minus can take H plus from water to form OH. Now again, it shows equilibrium. Shifting this further, it will convert into NHR, OH. Again, equilibrium. Now, by taking H plus, it may convert into OH2 plus. Then this nitrogen donate lone pair of electrons, making this H2O2 leave. Again, carbon bond, double bond N, H, R, right? Positive charge over nitrogen. Now again, H plus is lost. Finally, it will convert into double bond N, R. Anyhow, same only or not? But we have written in more number of steps, nothing there, same based on, right? Any questions in it? I am taking one example. CH3CHO, I have taken acetaldehyde. This acetaldehyde is allowed to react with NH2OH. Now tell me, among nitrogen and oxygen, which is better donor of lone pair of electron? Nitrogen have lone pair, oxygen also have lone pair. Which is better donor? Oxygen is more electronic, so it will pull electrons. It will not donate easily. So which is better donor? So if nitrogen donate lone pair of electrons here, then here converts into OH. Again, remove H2O. Means indirectly can I remove 2 hydrogens from N and 1 O from oxygen? Or indirectly, can I remove these 2 hydrogens and this O? Then what is the product? CH3, CH, double bond, N, OH. Respond. What is this group called as? Double bond NOH group. Oxime. Yes or no? One note here. In case of oxime, so let me see one named reaction. Beckmann rearrangement. one important name reaction. Beckmann rearrangement, right? Just a moment. Observe. Aldehydes are ketones with NH2OH. What you got? Oxime. Oximes with acids. What you got? Rearrangement product or not? Caprolactam, amide it converted to. So oximes in presence of acids rearranges to amides. We call that reaction as Beckmann rearrangement. Any questions, sir? Right? So just a moment. Beckmann rearrangement, right? Here right now. Under Beckmann rearrangement, it is catalyzed by acids. Catalyzed by acids, weak acids, maybe H3PO2 or dilute H2SO4 or maybe SOCl2 or maybe PCl5, etc. All these catalyze Beckmann rearrangement. So it is acid catalyzed transformation of amines to, is it amines or oximes, sir? Right? Oximes to amides. Response, sir. That we are writing it as N substituted amide. Will you understand the meaning of it? N substituted amide. Some substituent must be there on nitrogen. N substituted amide. Example: R carbon, R prime, double bond, N OH. Oxime I have taken. I am adding acid in presence of acid. Now H plus will go towards oxygen because nitrogen is a good donor, but it is double bonded nitrogen, more electronic. So nitrogen will not donate. So oxygen will donate one pair of electrons. So what you will get? R carbon, R prime, double bond, N. Can write it as OH2 plus now. Response, sir. Now the group which is opposite to that H2O will migrate over nitrogen. So the group which is opposite to it will migrate here, making this H2O to leave. Then what you will get? What would happen here? Migration of R minus, which is opposite to can I write as H2O plus, or can I write as a leaving group? Any questions, sir? Then what you will get? Again equilibrium. Can I write as R single bond carbon? Can I write positive charge now? R minus migrated. Then this carbon becomes electron deficient. Yes or no? So this becomes En, and here I got R prime. If you have positive charge over unsaturated carbon, it becomes highly unstable. That's why it will react with water again. The H2O is gone, that H2O will be donating lone pair of electrons towards this carbon now. So again that H2O will donate lone pair of electrons to that carbon. This H2O will donate lone pair of electrons to that carbon. Then what you will get? Again, equilibrium. What do you get now? R, C. Now, can I write after donating, you will get positive charge over oxygen. Therefore, can I remove H plus? So after removing H plus, what you will get? Can I write OH here? Double bond N, R prime. Any questions are in this? Then it undergoes a tautomerism. Then this hydrogen migrates from here to N. So tautomerize. After tautomerism, what you got? R, C double bond O, single bond N. This H came there, so it becomes NH, R prime. Now, is it N substituted amide or not? Response, sir. Is it N substituted amide or not? So we call this rearrangement as Beckmann rearrangement. So oximes in presence of acid convert to N substituted amides, right? So in tomorrow's class, we will continue, right? So I will take one more example and I will close Beckmann rearrangement reaction. I'm taking one example. Cyclohexone allowed to react with NH2OH followed by reaction with H plus. Now tell me what is the product. First, on adding NH2OH, what should happen? From here O, from here H2. So what you got? You will get double bond N, OH. You got oxime, correct? Huh? Oximes in presence of acid, what happened? It will convert into double bond N, OH2 plus, correct? Or then the group which is opposite to that leaving group should migrate over N. Means this has to migrate here and this H2O should be lost. Then what you should get? What I should get now? Now this 6-member becomes a 7-member with a double bond inside. Response, sir. 1, 2, 3, 4, 5, 6, 7. Is it 7-member ring or not? Just say something, sir. Yes or no? Right? Now, when this carbon got migrated over this double bond, whether I will get positive charge or not. And this group migrated from here to here, man. Then this carbon, this double bonded carbon gets positive charge or not? Right. After getting that, what I have to do? H2O has to donate lone pair of electrons. And H plus should be lost. Respond. Correct? Then what you will get? The same 7-membered ring. There is double bond here. And here I should get OH. Then tautomerism. What you will get after tautomerism? That will convert into amide. Yes, correct or not? No. In this amide, observe here. If this is carbon, next carbon is called as alpha, beta, gamma, delta, epsilon. So what we call it as epsilon caprolactam. Cyclic amides are called as lactam. Cyclic esters are called as lactones. Right? Lactones are cyclic esters. Lactams are cyclic amides. Is it cyclic amide or not? Now, this is alpha carbon, this is beta, this is gamma, this is delta, this is epsilon. So that's why it is called epsilon caprolactam. Right? So oximes are rearranged to N substituted amides in presence of acids. We call this rearrangement as Beckmann rearrangement. Any questions are online?
No, sir.
No, sir.
Better I will stop today's discussion here. So we are discussing about how aldehydes or ketones reacts with nucleophiles. That too with oxime it is over. Means with the hydroxylamine it is over. NH2OH is called hydroxylamine, no? With the hydroxylamine, they will form oximes. So that reaction is over. So other amines we need to discuss. Right? In next class we will see. Tomorrow also we have 2 classes. Correct or not?
Yes, sir.
Right, sir. So I will end today's session, sir.
Thank you, sir.
Yes,
Thank
sir.
you, sir.
Yes, sir.